oops. So this was what the handout looked like. It explains the same thing. It talks about the trees, okay? And what to multiply together to get what. We're going to go through some similar examples today, but just so that you guys can get used to it. All right. So this part's in your book, and if you're going to get the note guide, then it's on there, okay? So just in case you see the name of it later, it's called the counting principle or the fundamental counting principle. Is just this idea that if you're trying to find the number of ways you can choose or arrange things, you can multiply the number of options in each category together. Okay? So like if you own 3 pairs of pants and 2 shirts, then you have 6 possible outfits. Okay? And that's it. All right? So it just means you can multiply the stuff together. I'm going to go kind of fast through this slide just because this is literally from your book. Okay? So this part's right in there. All right. So as we're multiplying stuff together, we're going to start to see this symbol. So if you were in English class and you had to read this, okay, how would you read it? Yeah, like 5. Woo, okay? But that's not what it means in math class. All right? So this symbol for us is called the factorial symbol. So an exclamation point for us means factorial. And factorial means we're going to multiply that integer and every integer below it until we get to 1. So 5 factorial is how we would say this. We wouldn't say 5, okay? Say 5 factorial really means, oh, not that. It really means 5 times 4 times 3 times 2 times 1. Because if we multiplied it by 0, everything would 0 out. Fair question. Okay? All right. And the specific, and actually his question goes beyond that. So arithmetic-wise, it wouldn't make sense to have it go down to 0. But also the reason it doesn't go down to 0 is basically this was made for a very specific reason. Okay? It was just made as a symbol to mean this so they didn't have to write out a bunch of multiplication all the time. Okay? And the reason that they want a symbol like that is the questions that we're going to see coming up. So I'll touch on it again. And then I also want to mention here that 0 factorial is actually worth 1. Okay? And that's by definition. So when they defined factorial, so they're doing some problems, right? And they have to multiply out all this stuff. And they're tired of writing this times this times this, dot, 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 times this. So they say, let's use a symbol to like mean this. So they choose this. Okay, so this now means we're going to multiply all the way down to 1. And we'll talk a little bit more about why we stop at 1 there. However, in the calculation sometimes, the formulas we're going to see, this shows up, but it doesn't make sense to have it really be 0 in what we're trying to calculate. So they said, our only flaw is that when this shows up, it's supposed to mean 1. So what do? They say, well, since we defined this, exclamation point to mean factorial and this multiplication stuff, we're going to say when you see 0 factorial, it's equal to 1. Okay, so that's by definition in the way that they're using it. Alex?
We're allowed to have like a negative factorial, right?
No. So you'll never see a negative factorial. Okay? You will see only whole numbers. You won't see 5.3. You won't say -2. Okay?
Is there something that goes like the opposite way? Like if it's -5, then it goes -4, -3?
No. They don't have a symbol that means that. That doesn't mean you can't multiply those things together or indicate a pattern. But they just defined factorial. And again, all of those questions about why we wouldn't have a negative, why wouldn't we have one that climbs upward, all have to do with the types of problems that we use this to calculate that we're going to see in a couple of minutes. Okay? The multiplication helps us count things like we saw in the math moment. And basically, it's not like you would ever have 0 choices or negative choices. And we'll talk about that when we get there. Okay? So when you see n factorial, though, just how to take it from like a concrete number to a little more abstract. If n is the number, what would be the number below n, Julia? Good, n minus 1. And the number below that would be n minus 2. And you don't really know how far it goes, but it's going to go down to 1. Now, this is just important when we're trying to prove stuff or we're working in the abstract or we're trying to simplify things that have variables in them. Okay? So, factorial means multiply from that number down to 1. We only use positive numbers. 0 factorial is defined to be 1. So when that shows up, we're not going to zero everything out. We're just going to treat it like 1. Okay? So just a little bit of notation. All right. So this comes to like how to count things, all right, that have to be arranged. So an old website requires a 4-character password consisting of 3 numbers and 1 letter. Okay? So we're going to have this old website, 4-character password, okay, 3 numbers and 1 letter. A new website requires a 6-character password consisting of 3 numbers and 3 letters. How many more passwords can be made for the new website? So we have to have a way to count how many different passwords people could come up with here, how many different passwords they could come up with there, and then subtract them. Okay? Ideas about how we can count this, or questions that you have that need to be clarified before you could continue. Eric? Okay, good. So kind of like our sandwich, side dish, dessert problem. We took like, oh, there's this many sandwiches, this many sides, this many desserts, and because we're making a decision about a sandwich, a side, and a dessert, we're going to include each of those decisions multiplied together by the number of options in each spot. Okay, Julia? Yeah. Yeah. Yeah, and so this problem's a little bit vague. Yeah, so you'll see problems with different restrictions. The way that ours works. Okay, so 26 letters is important. There are 26 letters in the alphabet. And then digits. So it depends. So when you're making like license plates and stuff and how many different license plates you can make, it kind of depends, and sometimes they put restrictions like, oh, you're not going to use the letter O or I because it kind of looks like 0 and 1, and we want to differentiate. Now here they have none of that differentiation, okay? So we're going to assume we can use 26 letters anywhere that we're putting a letter, and yeah, we'll choose 10 different digits because we'll include from 0 to 9, okay? Now, again, if they put some restrictions on this problem, it would matter. Now, there's kind of something else we have to know about the way it's worded to be able to actually answer the question. Any ideas? Yeah. Mm-hmm. Right. So a decision we have to make ahead of time is like, is it, when they say it consists of 3 numbers and 1 letter, does that mean number, 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 letter? Or does that mean 3 numbers and a letter in any order that we want? Okay. So this one doesn't specify. So we would say any order. If that's the case, and it doesn't say we can't repeat, then basically how many options do we have to fill in a spot here? 36. If it doesn't say it has to be a number first, it just says it consists of 3 numbers and 1 letter, then we have 36 choices here. Then when we go to decide what's going to be the second thing in our password, how many choices do we have? 36. But not really, right? Well, 35 if we can't repeat it, but then we have to make sure 3 numbers show up and only 1 letter. And so if we say 36 choices every time, that doesn't quite make sense because that includes letter, 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 right? And that's not really an option for us. So the way we're going to do this problem is we're going to let it dictate the order. We're going to assume the order matters. So go up and next to it write the order matters, because we'll get into some other ways to pick it more substantially when we don't know if the order matters, okay? So then to simply count it, we need number, 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 letter, right? That's what it said? Say 3 numbers and 1 letter, okay? And of course a website wouldn't make a password like this because then people would easily be able to guess it with such like strict parameters on each one, right? So how many options would you have for the first spot? 10. And then for the next spot? 10. And the next spot? And the next spot? 26, okay? And you would multiply that all out to find your total number of possibilities, which is going to be, 26,000. Okay. All right, so we're going to put the same parameter on the new one. Now, I wouldn't give you this problem like this on a test. I would be more specific, because you'll see that as we get deeper and deeper into probability, there's lots of little questions you need answered before you can actually calculate the number of possibilities or the probability of something happening. So it says 3 numbers and 3 letters. So we'll say number, 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 letter, letter, letter. Okay? So for each of the first 3 spots, how many choices do we have at each spot? 10. Okay, so 10 things to choose from, 10 things to choose from, 10 things to choose from. Okay? Then we have to start picking letters. So we have 26 choices, 26 choices, and 26 choices. And if the numbers and letters had to be unique, meaning we couldn't repeat, this would go from 10 down to 9, down to 8, and then from 26 down to 25, down to 24, because we couldn't use the same letter we already had. Okay? But we're not going to put that restriction on it right now. So then, what does this multiply out to be? I trust all of you, but I'm just going to use a calculator because I can't differentiate what you're all saying. So 17,576,000 different passwords could be built that way. Okay? Yeah, so to get our final answer, they asked how many more passwords can we build on the new website. So we'll subtract, like Alex said. We subtract 26,000 from this, we get... Cody? We're going to get to that later in the chapter. All right? Because we're going to start talking about it today. And then we're going to have to ask a lot of questions about it to figure out exactly what we have to do. Okay? Using things called combinations and permutations. All right? All right, so counting principle, kind of figure out how many decisions we're making, how many options we have at each of those, and multiply it all together to see the many different ways we could combine all those things together. Okay? All right. How this can change a little bit and why they came up with the factorial and why it doesn't go all the way to 0. Okay? So let's say there are 7 students waiting for the financial office to open. Okay? So question 1, in how many different ways? This should say, can the students Okay, in how many different ways can the students line up at the financial office window? So there's 7 people sitting there waiting for it to open. Let's see, they see the lady walking up, and you want to predict how many different ways they could line up. Okay? How are we going to figure this out? Julia? Good. Basically 7 factorial, because how many people are there? 7. How many of them are getting in line? 7. So we have 7 spots in line to fill, right? How many people could fill the first spot? There are 7 options. Now, once that person has stood in that spot, how many options are there to fill the next spot? 6. And then the next spot? 5, 4, 3, 2, 1. Okay, so why doesn't factorial go down to 0? Because factorial came about to do these calculations. Okay? If we're doing these kinds of calculations where we're just trying to order a certain number of objects, we don't say there's 8 spots in line and like 7 people to fill them. We just want to know the number of ways we can arrange the 7 people, right? So that 7 spots, 7 people, we would have 1 person as our last choice, and then that would be it. That would be the number of arrangements. We wouldn't go on to any more spots if there's no more people left. So that's why our factorial stops at 1. Because it's made to do this kind of calculation. This is where this problem shows up and why they would get sick of writing out multiplication if the number is like bigger than 7. So this could also be called 7 factorial. there actually is a factorial button on your calculator. In the math menu. That's good. I need to let you guys know where it is on here too, because future AP tests, no iPhone will be allowed to take the AP test, okay? So in the math menu, once you go in there, if you scroll all the way over to the right, one of the menus is labeled PRB, which stands for probability. And on this menu, choice number 4 is the factorial symbol. Okay? So you can actually type in 7 factorial on your calculator and not have to type in 7 times 6 times 5 times 4, etc. Okay, so 7 factorial comes out to be 5,040. So those 7 students could line up in 5,040 different ways. Isn't that nice? Okay, aren't you glad you didn't have to count it by actually listing out all the arrangements? Okay. Now, how that can change slightly, what if I don't care about the entire line of students? Okay. What if instead I care about only the first 3 spots? So what if I just want to know about arranging the first 3 spots? What is that calculation going to look like? Cody? No. Albert? Good. 7 times 6 times 5. Did I change the number of students waiting at the financial office? No, there's still 7 of them. So how many students could I have be first in line? 7 choices. Once that one is decided, how many people could be second in line? 6 different options, right? Once that has been decided, how many people are there to choose from to fill the 3rd spot? 5 different options. So it's going to be this calculation right here. Okay? Notice it's kind of like part of this, but it's like it's cut off this other part right here because we only cared about the first 3 spots and not the rest of them. Okay? So first of all, the answer to that is going to be 210. I almost got my calculator kind of sad. Okay, so it's going to be 210, all right? And then I want to talk about what we just did. Yeah. Mm-hmm. Yeah. Okay. All right, so let me see what's on this slide. Yeah, don't want to show you that yet. All right, so what you guys just calculated are these things called permutations, okay? So permutations are ways to order things. And so there's a formula that exists for a permutation, okay? So I want to just show you how they got the formula, then I'll put it up here so you can write it down. All right? So basically, if I have 7 things and I want to arrange them, all of them, we know that that comes out to be 7 factorial. And mathematicians want to use that factorial notation because if it's like 100, they don't want to write out everything, right? But if I only want to arrange 3 of the objects, so this is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so let's say I have my 7 factorial, but I only want to look at the first 3 spots. Okay? Then I want all of this essentially to get canceled out. And it's a multiplication problem, right? So how would we cancel out all of that stuff? We would divide by this, all those factors. How can I nicely call this without writing out all these factors? 4 factorial. So when we were doing the 7 times 6 times 5, we were really taking the entire line of people and then like canceling out the spots that we didn't want. Okay? So in a permutation problem, your formula is going to look like this. How many things are involved in the problem? Calculate that factorial. You don't want all the spots? Cancel some out. How many to cancel out? Well, we wanted 3 spots. Did we cancel out 3 things? No, we actually canceled out 4. How are 3 and 4 related to the fact that we had 7 items in total? They add up to be 7. So if this is 7, okay, and I take away the amount that I want, like 3, 7 minus 3 gives me 4. All the stuff that's left that I don't want, right? So that's what we're using in the denominator. So basically, the way we'd calculate the whole line, and then some stuff to divide off for the factors that we don't want. How many we want to divide off is our total minus the amount we want. I have 7 things. I want 3 of them. 7 minus 3 happens to be 4, and it'll cancel everything from the 4 down. Okay? So that's how it will work. So this is called a permutation. So here's the notation that you'll see. So first of all, permutation is what you want to do when you want to arrange things in an order and you want to count the number of ways that happens. We deal mostly with linear permutations, meaning we're talking about arranging them in some sort of line, okay, or looking at them in kind of a linear fashion. That's how things are ordered to us, right? If there's a first and a last, it's kind of a linear type of thing. So the formula looks like this. This is what we just talked about, right? Okay. You calculate that whole factorial, and then you do this little thing that you're dividing by to cancel off any of the spots that you don't really want to calculate for. Okay. What these things stand for, the N, is the total number of things involved in the problem. Like how many students were waiting at the financial office? 7, right? Okay. The R is the number you choose, or how many spots you want to fill. Okay? So when we did the whole 7 factorial, we were doing 7p7. Okay? Meaning I have 7 spots, and I want to choose 7 people to fill them. But then when we only wanted to look at the first, second, and the third spot, we were doing 7p3. Okay? And that means we had 7 spots, but we only wanted to look at the number of ways to fill 3 of them. Okay? On the calculator, that same menu we were in before, it actually has an NPR button. Okay? And so what you'll want to do, if you wanted to do 7p3 on the calculator, you would type in 7. Then you would go get the NPR from the probability menu, and then you would type 3, and it would do the whole calculation for you. Okay? Now, you'll probably be able to use a calculator on your probability test, given the calculations we have to do throughout this unit. However, I will ask you a question that involves you either to show or to explain to me about this formula so that I know you know it, okay, and how it works, even though you can use your calculator to do some exact calculations. Minchao? Permutation. Okay? Is this okay with everybody? So the permutation is the same thing as the counting principle if you're trying to arrange stuff in a line. It just gives us a quick way to note, hey, there's this many things and I want to look at this many spots or choose this many of them. Okay? But order is really important in a permutation. It's all about how many different ways you can order things. Okay? All right. So in how many ways can you arrange 9 CDs, one after another on a shelf? So when you want to use, if you're not sure if you should use permutations, you should look for things in the problem that indicate that order is involved. What words in this problem tell me that this is about ordering? Alex? Good. Arrange. If they just said, oh, how many ways can you get 9 CDs off of the shelf or something, and there was more than that, that wouldn't be about order, right? But we're arranging them, meaning we're specifically putting them, and they're making a point to say it again, like one after the other on the shelf, so you know it's like a linear order or arrangement of things, okay? So how many CDs are there? 9. How many are you ordering on the shelf? 9. So what kind of calculation do you need to do? Just a 9 factorial, okay? It's really the same thing if you did go through this, just so you know. Because this would look like 9 factorial over 9 minus 9 factorial, according to our little formula. Now, this might be like concerning to you. You're like, oh, Ms. Dahl, 0 in the denominator. But this isn't 0 in the denominator. Good. It's 0 factorial, which is really 1, which means it's 9 factorial. And I'm going to leave my answer like that right now, assuming you guys could go push the button on the calculator and get the answer. Okay? I'm more concerned about that we know how to get the answer. All right, in how many ways can a first, second, and third baseman be selected from 8 players? Now, baseball players, okay? A willing suspension of disbelief, I guess, like your English teachers might say if you read a story that's unbelievable or watch a movie, right? I if there's only 8 players, first of all, there's like 9 players on a baseball team, right? You need 9 people on the field, right? But if there's 8 players, there's probably 1 first baseman and 1 second, right? That has already been determined, okay? But let's say this is like my son's like first experience with baseball, you know, like the little city t-ball things they can go to, okay? And you're given 9 kids and you have to go put them on the field and they've never played before. How many ways can a first, second, and third baseman be selected from 8 players? So what's this calculation going to look like? Eric? Okay, good. 8 factorial divided by 5 factorial, or in other words, it's a permutation because we're ordering the players. We're saying, hey, you're first baseman, you're second baseman, you're third baseman. Those different titles dictate order because if I choose the same 3 people in different ways, then their titles have changed, right? Like if I go first base, second base, third base, that's different than first base, second base, third base, even though I chose the same 3 people, right? So titles make order matter. So this doesn't say arrange, but order matters because if I call you first baseman, that's different than second baseman, okay? And so I'm choosing 3 out of the 8 people to fill those spots. So like Eric said, this would be 8 factorial over 8 minus 3 factorial. This is 8 factorial over 5 factorial. Now, you don't go, oh, that's a fraction, like we can't do the factorial. The 5 is not allowed to come up and divide the 8, because 8 factorial really means what? A crazy number, but like just draw it out for me. Yeah, like 8 times 7 times 6 times 5 times 4 times 3. But in the denominator, what do we have? 5 times 4 times 3. So when these simplify, what are we going to be left with? Times 7 times 6. And everything from 5 on would have canceled out. Same factors in the numerator and denominator. Okay? So a lot of these can be done actually without a calculator sometimes because you're not really doing as crazy of a calculation as you think if you know how to simplify it ahead of time using factorials. Okay? Alex? Yeah. So again, it comes back to why 0 is not included. So 0 on an arithmetic thing, we said, well, 0 is not included because everything would be 0. But on like a theoretical kind of idea, 0 wasn't included because remember, factorial is coming about to help us understand this idea of filling these spots, right? So think about the 7 people in line, right? 7, 6, 5, 4, 3, 2, and I do have 1 option left to fill the last spot. So because it's about counting options, they include 1. But I agree with you. In the arithmetic part of it, 1 doesn't seem to play an important part, right? All right, so you can also do this to, how many of you guys have ever done those things? I think they're in like older like puzzle books. They like give you a word and say like, how many words can you make from this word? And you like try and like arrange the letters, okay? So there's a way for us to count this because we could say, well, there's this many letters and I'm choosing this many of them to make my word, and we could talk about a permutation, right? So let's say we had to use all the letters in our word. So we have the word elliptical, okay? It's good for like demonstration purposes because it's long and has multiple letters in it, okay? So elliptical has how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So how many ways are there for me to order the 10 letters of the word elliptical? 10? Let's say it doesn't have to make a new word, but I can just like rearrange the letters. How many choices do I have for the first letter? 10. And then once I've chosen that letter, how many choices for the second letter? 9. And if I'm filling all 10 spots, we're just going to say then 10 factorial. But here's the problem. Let's say I take the word elliptical. Ready? Everybody close your eyes. I'm going to magically rearrange it. Okay, poof. Okay, I rearranged something in it. Does it look any different? Oh, I changed the L's. Okay, but is this really a new permutation? Is it? Are those L's distinguishable? Can you tell them apart? No. Not unless they were like L1 and L2 and L3. Then we could tell them apart, right? And so then this would be the right answer. But the fact that we can't tell them apart, every time we just switch L's, those weren't really new permutations. So we counted this many, but there's some stuff we have to divide out because we counted too many. Okay? How many L's are there? 3. So how many ways could we just switch up the L's without moving any of the other letters? 3 factorial. 3 choices for the first L position, right? 2 choices for the second L position and 1 for the other. Those all have to be divided out because we counted those as 6 choices, 3 times 2 times 1. But really, those are all 1 choice. Okay? Is there any other duplicate letters up there? I. How many I's are there? 2. So how many ways are there for me to rearrange the I's? Just 2 or 2 factorial. Okay? And then this is how you'd figure it out. So you'd basically take the amount of letters and say, yeah, here's how many ways I can arrange them. And then you'd say, there's 3 L's, so I'm going to cross off all those duplicates. There's 2 I's, so I'm going to cancel out all those duplicates. After I divide those out, then I'll have the true number of ways I could arrange the letters. Okay? Yes? Mm-hmm. Yeah, you would just have to simplify and multiply it out. Yeah, it's not as simple as the other one. The numbers aren't as close, so it doesn't work as well. All right. So this is not a hard problem, but it's going to transition us into a new idea. Okay? Let's say you have 4 letters, A, B, C, and D. Okay? Amazing, right? And the question was, find the numbers of ways to arrange any 3 of the letters. So how many objects do we have? 4. How many are we choosing in our arrangement? 3. So how would we do that? 4p3, or the calculation is going to work at, how many choices do we have for the first letter we choose? 4, and then, okay? And so that all, no matter how you put it, or if you do 4 factorial over 4 minus 3 factorial, which only cancels out the 1. Anyway, you end up with 24 arrangements, okay? Arrangements. A, B, C, different than C, A, B, right? Arrangements, order, okay? Now we want to find the number of ways to grab any 3 letters, okay? Why is just grabbing 3 letters different than arranging 3 letters? How is that different? So let's say in my class, I want to elect a class president in our class, a class vice president, and, I don't know, a class commissioner or something for our math class, okay? All right, and so then I walk up here and I say, oh, I've selected 3 people, Bailey, Allison, Claire. You guys are it. President, vice president, commissioner. Okay? Now let's say I do the same thing again. I select the same 3 people, but I say president, vice president, commissioner, and they just got different titles. Is that the same arrangement as the first one? No. It would mean different things when I handed the paper to administration and said who was who, right? Now let's say I didn't want to give anyone a title. I just wanted a committee of 3 people, very democratic, right? I just want a committee of 3 people to go and represent our class, okay? And so I go Bailey, Claire, Allison. Okay? Well, if I say Allison, Claire, Bailey, have I changed it? No. So do we see the difference between arranging and just grabbing? Okay? When we grab the group, it doesn't really matter the order. If they made it in the group, they made it in the group. They're all the same no matter which order I put them in. If I want to arrange them president, vice president, commissioner, okay, or first, second, third, then it's very different. Okay? So what they're doing by saying, what if we just want to grab any 3 of them, is they're taking away the order aspect. We're still picking a group of 3 out of 4, but the order no longer matters. Okay? So when we think about this, if we're just going to pick a group, we could have the group A, B, C, okay? A, C, D. What other groups of 3 could we grab? A, B, D? B, C, D? Anything else? DAB, already have it, right? Because we're just grabbing a group of 3. Anything else? Okay, so if we were arranging them, there were 24 possible ways to arrange the group of 3. Now that we're just grabbing a group of 3, how many different ways did we get? 4. Okay. A lot less, right? Because before, this group could be rearranged a lot of different ways, okay? And then that's how it got counted. So what's happening here is this. We're taking our permutation calculation from before, okay? But we're getting rid of the bunch of the options, right? Before this was 24, okay? All right? But we actually ended up with 4 ways we could just grab a group. 24 divided by what would be equal to 4? 6. This 6 is significant. It's not just random. How is 6 related to the fact that we were choosing 3 objects? Eric? Okay, because 6 is 3 factorial. So remember, if you wanted to arrange 3 things, what's the number of ways you could arrange the 3 objects? 3 times 2 times 1. We took that option out, right? We said when you pick ABC, you've picked ACB, BAC, CAB, right? All different arrangements of those letters. So no more 3 times 2 times 1. Instead of it being this now, we just said, like, yeah, it don't matter. Okay? There's one way to arrange all of them. They're all the same no matter how I look at them. So this part is being taken out. All those options are being canceled out of our previous options. Okay? It used to be 24. Now cancel out all of these. So we take the previous calculation and we divide it by the arrangement of those objects. Okay? So this gives us a new formula. It looks really similar to the old formula because here's the old formula. It just has this extra piece right here. Notice that's the same number you're using right there. So it's not going to be that bad. We don't have to introduce a new variable or anything like that. So this is called a combination. Okay? Combination. So instead of P, they use the letter C. Okay? It has the same permutation formula, except for it divides a bunch of extra stuff out because we don't want them arranged anymore. We just want them in groups. Okay? Can be found in the same place in your calculator, just as NCR instead of NPR. So this is important when order does not matter. Okay? We're specifically going to use this when order does not matter. Does everybody understand that? Does everybody have the formula? Pause it. So nothing changes about what N means or what R means. It just means we're choosing a group where order doesn't matter. Matt? Yes, like the committee versus everybody having a label or an order to them. Okay? So in this problem, you have 20 songs on your MP3 player. You have time to listen to 4 of the songs. In how many different ways can you select 4 songs if order doesn't matter? So this is going to be like, what 4 songs did you listen to? Not, what's the order of the 4 songs you listened to? Get the difference? So it's not about which song was first, second, third, and fourth. I just want to know, what 4 songs did you listen to today? Okay, so it's a group of 4. It doesn't matter which one you chose first, second, or third. So is this a combination or a permutation? Combination, because we don't care about the order of the song. So this is a combination. How many songs are there total that we're choosing from? And how many did we choose? 4. And so the formula says that means 20 factorial over 20 minus 4 factorial. And then because it's a combination, the extra 4 factorial in there right there. Okay? Now, you might think like, oh, I can never do this without a calculator. But this isn't that bad. Okay? Right here, the 20 factorial and the 16 factorial. What does that end up simplifying as? 20, 19, 18, and 17. It's not pretty, but could be worse. Okay? And if you had to do this by hand, what I would start doing then is like canceling common factors, okay, and getting it kind of as narrowed down as I can. Like, oh, 4 goes into 20 5 times. 3 goes into 18 6 times, and 2 goes into 6 3 times. And then I just need to multiply these 4 numbers here to find my final answer. Okay? And I'll write it up there for completion's sake. Okay? Or you could use the NCR button and do 20. But you have to know the formula. I will ask. Okay?